Okay, welcome back and welcome to section 18.1. It's titled matrices. That's because we're headed into this section of linear operators. It's a pretty short section because I think the author is convinced you know about matrices by now. But anyway, we will cover some topics of matrices again, but we're covering them with the intent of heading towards linear operators. And actually, I think I'll share my one of my ODE's course videos on linear operators as well to try to reinforce what's actually happening here. And where we're headed, but we'll just go through the book because that's the section we're on today. So recall a matrix, and here they're using the letter T for a matrix, and that's because we're considering them as linear transformations. So T for transformation on R3 to R3, it just inputs a vector and outputs a vector. I think you all recall these sorts of ideas. But the important thing is this next line, linear. Linearity is any map from a vector space to itself, which satisfies this, is called linear. And what do I mean by satisfies this? This is a very important property called linearity. What it means is that it quote unquote behaves like multiplication. Because what's happening here is the T is, if the input is U plus alpha V, and the T distributes to U and alpha V. So say distributes to the U and the alpha V. And it also, notice that the alpha is on the backside of the T. So the alpha also can pull out of the V term. And that's called commutes with scalars. So the T can pass through the alpha, and it can also distribute over the plus. And that's exactly the sort of property we have when it comes to multiplication, right? Multiplication has the nice property of distributing across a plus sign, and it also commutes with any other numbers that might be sitting around. So this is really where we want to put our headspace for the rest of the semester. Okay, so our headspace should be, does this particular transformation satisfy the particular properties that it distributes over plus signs and commutes with scalar multiples? And it just so happens that matrices are kind of our classical example of one of those. When we were considering T as a matrix, if we consider it a matrix square bracket A, I guess, if we consider T as the matrix square bracket A, we actually just use a new notation, right? It's no longer T with an input of V, it's a matrix against a vector. So this is considered like matrix multiplication on the vector V equals W. So there's just a slight notational difference because these are two representations of the same map, but you can interpret them a little bit differently. If we jump to linear equations, these are important because they're the equations which are really easily solvable. And maybe I'll make this a little bit more clear. What is that? An example of something like that would be like 1, 0, negative 1, 2, 1, 2, negative 1, 0, 0 times x1, x2, x3 equals negative 1, negative 1, negative 1. Like that's a perfectly valid matrix equation. I'll shift it there so you can see it. That's a matrix equation where the unknown is a vector, right? We're searching for an unknown vector. We have a matrix against the vector equals another vector. And I think a lot of you remember how to solve something like this from your last semester. You would solve it by inverting the matrix, right? How do I get rid of maybe the matrix right here? I get rid of that by inverting it and multiplying both sides by the inverse, right? So we solve linear equations. And this in this case is in high dimension, by inverting the linear map, which in this case was A, right? We invert the linear map A and multiply both sides by it. Okay, so, in my situation, I would probably just input that matrix into Wolfram Cloud, calculate its inverse, and act the inverse on negative 1, negative 1, negative 1. And that would give me my solution x1, x2, x3. So something that's useful then, when it comes to matrices, are the eigenvalues. And maybe this wasn't stressed so much as to why eigenvalues are useful, but what the current section is trying to stress for us is that eigenvalues are useful because they make inverses easy, very, very easy. Because as long as I've satisfied an eigenvalue equation, this is a very particular E. Okay, this is not going to be true for any input E there. But given an input E, I can actually compute the inverse matrix on the input E by just computing the multiplicative inverse of the eigenvalue. And it turns out that, why would that make finding an inverse easy? Well, it's no surprise that they're using e's here, e not only for eigenvalue, but also for e as in the basis elements e. If I can find a basis of eigenvectors, then inverses are easy. So really, eigenvalues are useful because they make inverses easy given a basis of eigenvectors e. Okay? So this is something else that we want to be thinking of for the rest of the semester. Can we find a basis of eigenvectors? Basis of eigenvectors is the most important thing in all of linear algebra, and actually in all of most of higher level math. Okay, so basis of eigenvectors is the most important thing we can think of for the rest of the semester. Because if we have a basis of e's, then A on the basis is inverted by inverting eigenvalues. And since it's invertible on a basis, it's actually invertible everywhere. So when can we find a basis of eigenvectors? This is exactly the property of diagonalization. So diagonalization is the process of finding, so lambda here is the diagonal matrix of the matrix A, where we have some sort of transformations P, and basically the P's, right? The P's are matrices of eigenvectors, a basis of eigenvectors. So you take a matrix as a basis of eigenvectors, you take its inverse, and you kind of put that on both sides of A. You recover a diagonal matrix of eigenvalues. And that makes your life really easy because the inverse, all you have to do is invert the diagonal matrix, which gets inverted by only inverting the eigenvalues. And then you can find A very, very easily, A inverse, very, very easily. This is actually notated poorly. That should be the inverse right there. But aside from that, you can find inverses of A very easily by inverting the diagonal matrix instead. Okay, so the next section is on adjoints, where I think you probably covered this already. There's this thing called the Hermitian adjoint or Hermitian conjugate. That's sometimes denoted with a dagger, which is what we have here. That's the cute little math symbol known as a dagger because it looks like a pointing down dagger. And then over here, what it is it's the transpose of the matrix and you take its complex conjugate. So that's the Hermitian adjoint. And then the special thing about some matrices that are known as Hermitian or self-adjoint is that their Hermitian adjoint is equal to themselves. And these matrices are special. Why do we care about them? Special because the diagonalization exists. Okay, so this is a really easy way of checking whether or not a matrix is diagonalizable before we go ahead and try to diagonalize this. You might have the question, why not just try and diagonalize it and see what happens? Well, if the matrix has 30,000 entries in it, I don't think you want to try to diagonalize it. It would be a lot easier to just check. This is a much easier operation to do with 30,000 entries than it is to try to diagonalize it. In the event that it's true, it's valid, this one's valid, then you have to go and diagonalize it. But in the event that it was false and this weren't equal to its Hermitian adjoint, then you just saved yourself a lot of time from trying to diagonalize a 30,000 entry matrix. So that's really the reason why we care maybe about something like this. And in particular, something else that's very special about these is that all of the eigenvalues are real. Okay, so if all the eigenvalues are real and it's diagonalizable, then we have really nice properties. Anyway, that's actually all I have for today. I will share my other video, though. I think you should watch the other video to get a little bit more background with all of this. It'll be linear algebra focused, but that's all. Anyway, see you in class. Bye.